In this module, we'll discuss the terminology to be used throughout the course. The first term to be defined is critical infrastructure. As the term implies, it is infrastructure that's critical to the well-being of a nation. That infrastructure can be, for example, the power grid, right? Electricity that goes to our houses. Without electricity, then a city wouldn't be functioning properly. Transportation is critical infrastructure. Water, both drinking water, water treatment, wastewater treatment, communications, and many other things, right, we can think of. Officially, the definition of critical infrastructure refers to sectors whose assets, systems, and networks, whether physical or virtual, are so important that anything that happens to them would have a tremendous effect to the city. I already mentioned power, energy, right, or communications. The US Department of Homeland Security defines 16 sectors as critical infrastructure. I already mentioned energy and communications, but there are many more. For example, chemical processing, dams, emergency services, transportation systems, we mentioned water, nuclear, reactors, critical manufacturing, financial services, and so on and so forth. So these sectors form critical infrastructure. Another term that I've already been using is industrial control systems, or ICS. And industrial control systems are actually the systems that control the corresponding industries. They appear in all sorts of sectors, from critical manufacturing to nuclear plants, power systems. You can think of ICS of these devices, these small computers, that they're there in order to control some part of the process, right? They receive an input from a sensor, they do some calculations for control, and they produce some behavior, some actuation, again, to respond and control the process. So ICS encompasses the systems that are used for controlling the industrial processes. Industrial control systems, or ICS. And we already saw before IT and OT, the differences, information technology, operation technology, right? We can think of ICS as a subset of OT, even though the terms may be used interchangeably in the literature. Sometimes instead of OT, ICS, or ICS, OT. ICS is more of a subset of OT, that ICS mostly focusing on the system side, right? Well, OT is everything besides the systems as well, which, for example, will include the human factor, right? Social engineering, anything that has to do with the human operators, that's part of operational technology. While ICS is an umbrella term for all the systems used in critical infrastructure, there's still some distinction in the specific type of industrial sector that the ICS are controlling. The two big ones is, you can see on the left side, manufacturing and distribution. So the difference between the two is that manufacturing ICS, either process-based or discrete-based, refers to something that's confined geographically, right? We may be talking about a chemical processing facility that everything takes place in one factory, in one location, right? And there's no dispersion of assets geographically. So here we have a system, a simple system conveyor belt that is being controlled by several controllers, but anything within this manufacturing process happens, again, within the same physical location. On the other hand, distribution ICS refers to systems that are geographically dispersed, and a prime example of that is the power grid. So the power grid has different components, from generation, where the electricity is being produced, to transmission, that is transmission of electricity over long distances, to distribution, where the distribution of energy and power starts, and then consumption, that's the end customer. So in this case, these are very far away from each other, right? Many miles away. This can be in location, and you have over 100 miles cables to substations, and then to an actual city. And it's important to understand the distinction, because for the different ICSs, right, manufacturing or distribution, we have to think about security differently. When something is geographically confined, we're not really worried, for example, about the remote communications. But in the case of distribution, for example, the substation can be far away, can be unmanned, so there's no one there to check whether someone is physically entering and trying to cause some kind of an attack to the system. And these also imply more remote capabilities, right? So you want to access them remotely. There's no sense of an air gap, right, when we talk about distribution ICS. Well, here we can think of an air gap because we have a building that could be locked with access cards, right? Here the individual buildings may be locked, but there's open air communication somehow, so you can connect, the substations can communicate to the control center and send information back. So an attacker can interfere with a communication. If it's radio frequency communication, maybe they can jam it, right? So the way we think about security here, we can think maybe integrity attacks on the communication, that it's not the same here, right? Someone probably needs to physically enter in order to cause some kind of a disruption. Of course, I don't imply, and it's never been implied, that this is more insecure, right? It's all about doing a good job in securing. So if you're afraid, if in your risk assessment you realize that substation to substation communication is a critical part of your ICS, of your operation technology system, then you add security to it, right? You may add encryption in the communication. You may add integrity mechanism, right, to make sure that the messages, you may add authentication in the communication channels between the two. And, here we may have the illusion of the air gap, and someone might think, okay, that's a locked factory, so I don't need to worry about security. And at the end, the manufacturing asset could be more insecure because of all the myths we discussed before. So to conclude, ICS can be broadly seen as, again, manufacturing, geographically confined, and distribution, geographically dispersed assets. And we need to approach security differently for the two types. Another term that we'll use a lot in this course is the term control loop. And the loop refers to what actually we're used to, something that loops over and over, and control here refers to the control of some part of a process. So this control loop starts with sensing, right? So you have some kind of physical phenomenon, you're sensing, you're measuring in a way, and based on this measurement, a controller receives it as an input and will calculate something in order to produce some output. And this output is given to an actuator that will control something like a valve, for example, in this case. And the control of the actuator is causing the measure variable to also change properties, right? To change actually the values. So in case we're measuring water flow, for example, here the sensor senses the flow, the rate of the water, and the controller needs to stabilize that, right? It needs some constant flow, so it asks the actuator to open the valve or close it accordingly to some extent. And once the valve is being adjusted, then the flow rate changes and then is being sensed in a different value, and there could be some fluctuation that we're trying to stabilize, for example, right? A concrete instantiation of what I just described can be seen in this slide. I have an example that we have a flow controller, right? And the controller receives some input. So the input is the sensing of the flow rate. So there's some kind of a sensor that is being added in order to measure the flow rate, right? How fast the water moves through the pipe. So this sensor, this flow transmitter, is actually giving the value back to the controller. The controller has some kind of a computation mechanism inside, some kind of a control computation, that given the flow, it will produce some kind of appropriate positioning to the flow control valve. So you can think of a pipe that are measuring the rate at some point, and at some other point there's a valve that you can turn in order to reduce or increase the flow of water. And you may want to keep it steady, or you may want to fluctuate it according to the unique what's happening actually in your control process. So again, that's a loop, because you take the input, you control, you actuate by moving the valve is causing a different flow. So that changing the valve, changing the rate. So the rate is different. There's another input to the controller reads it and produces another output for the actuator, and so on. So this is the loop, right? Input, control, actuation. Input, control, actuation, sensing, control, actuation. This example also is a good example of cyber-physical system, right? That the cyber component is the communication from the sensor to the controller and the controller to the positioner, right? But in this part, there's a mechanical component. So the positioner is creating some kind of a physical effect to the valve, right? To open it or close it accordingly. So we can see how from the cyber world, you can go to the physical world, right? By actually adjusting the actuator, by adjusting this positioner to do some act. For example, you can abruptly stop the flow, and maybe you'll create some kind of an effect that will destroy the pipes by the water moving too fast, sudden block, and then you may have some mechanical damage because of the cyber effect of closing the valve very quickly. So the control loop is the main component of an ICS architecture, right? The control loop is what we saw now: sensor, controller, actuator. But there are more things in a typical ICS architecture. And one of them is the process itself, right? Because besides your effects on the process, what the controller decides and accordingly actuates, the process itself may have disturbances, right? Depending on what the process is, you have also external factors affecting it, and then you have to take appropriate action in order to make sure that your process is steady. A process example appears on this slide, physical process. So here, this is a graph of desalination. Desalination is the production of fresh water out of seawater. And it's very important to regions that don't have access to fresh water. So the idea is that the physical process takes seawater in and produces two things. One is fresh water, and the other one is brine, which refers to actually very salted water. So the brine has to be discarded somehow, and the fresh water can be given to households for consumption. This is a continuous process. Seawater keeps flowing in, and fresh water keeps coming out, and the byproducts, brine, also keep coming out. So the way this desalination, there are different ways you can actually remove salt from water. This one is membrane-based, and specifically it's called ion concentration polarization desalination. In this process, you bring current to the water flow, and this current is charging the salt ions, allowing the membrane to separate them from fresh water. So with this process, you can separate the salt from the water and have the distinction, the separation that you're targeting. In this example of a control process, there are disturbances, right? So the seawater, you don't know its exact salinity. It might fluctuate throughout the operation of the plant. So you have to be adjusting the voltages dynamically, see how the separation works, and then see if you have the proper flow of water and brine coming out as expected. So by sensing the separation rate on the membrane, you can adjust the actuation of the system accordingly. So that's an example of the control process, right? And sensor, control, and actuation. Another very important parameter, another very important component of the ICS architecture is the HMI, right? And the HMI stands for human-machine interface, and it's the way an engineer can get some visibility to the process in a usable form. You cannot just observe equipment, right? You have to have some form of a graphical interface that allows you both quick access and quick understanding of what is happening in the process. In this slide, we have various examples of HMIs from different industries, from the power grid to water plants or to simpler boiler control. And this HMI, as an example here, it gives visibility both to the engineer to see what is happening in the process, but also gives some very simple control if you want to turn something off, like the pumps here, which are closed, which are running, you want to enable a few things and see what's happening in the process. So you have a full visibility, both for monitoring what is happening in the process and for controlling it to some extent. HMIs are very critical parts of industrial control system, especially for cybersecurity, because they are the interface to the control system. And the HMI would typically run on a regular computer, right? You have your regular Windows machine having this interface that the engineer can use to control the process. So if that runs on a Windows machine, you can imagine that regular Windows malware can arrive to that machine, and then if it's an OT malware, can find the corresponding process, hijack it, and then use it to send commands to the control system. And that's exactly what Stuxnet did. It went to a Windows machine that had an HMI interface and a connection to the PLC, and used that connection in order to both hijack the PLC to do something else and to fool the operators into seeing the wrong values coming in to the HMI. So they wouldn't understand that the centrifuges were not spinning properly.